All right, everybody. We're going to go ahead and get started. Thank you, everyone, for being here in the room and online. We are very excited for today's talk, so thank you for coming out. My name is Cinnamon Moffett, and I'm the Research Program Manager here at Oregon State University's Hatfield Marine Science Center located in Newport, Oregon. For today's event, if you are online, your cameras, mics, and screen shares have been turned off, but we do have somebody here, her name is Roseanne, that is monitoring the chat. So if you have any questions or any technical issues, please put them into the chat box and we will either ask those questions at the end or we will address your technical issues as soon as we can. For those folks in the room, if you haven't been to one of these before, because it's a hybrid event, to ask a question, we do ask that you have a mic. So that means that if you have a question at the end of the presentation, just raise your hand and I get to run around to get my steps in and bring you the mic, or you can go to the mic stand that's off to the side there. Either way, we just ask that you use the mic stands or the mics to ask the questions. Okay. As most folks know, if you feel the ground moving, you are in a vertical evacuation structure. So we're going to go to the roof of this particular building. I think you're going to hear a little bit more about some of those other things today, just a guess. But we are excited that you are here. Wanted to just let you also know that today's event is being recorded. So if you would like to share it with others that weren't able to be here, it will be on the past HMSC past seminar page in a few days. So you can go ahead and find it there and share it out. Wanted to promo next week's seminar, same place, same time. We have Jess Hoff, who will be here to talk about marine reserves in a changing climate. So if you are interested in learning a little bit more about that, our local marine reserves has been doing a lot of work for their 10-year report. So it'll be really interesting to get a little bit more information about that. So you can join us next week on Thursday here. But why we're all here is for today's presenter. And so I just want to do a quick introduction of Dan Cox. Dan Cox is the CH2M Hill Professor with the Civil Engineering at Oregon State University. He has his bachelor's, master's, and PhD from the University of Delaware in Civil Engineering. His research focuses on community resilience to coastal hazards, including things like tsunamis, hurricane surge, wave inundation in the built and natural environment. And he conducts research on tsunami and wave impacts to near coast structures, tsunami evacuation and life safety, sediment transport and erosion, and natural solutions to coastal hazard mitigation. And so we are excited for today's presentation. And so I'm going to hand it off to Dan.
I think so. Hopefully everybody can hear me. Thank you, Cinnamon, for the kind introduction and for the invitation to come out here. Very excited to be here. In my job, I get to talk a lot about this building. I do a lot of work in tsunamis. I've worked with the American Society of Civil Engineers to help develop building codes for tsunami structures. And it's a great honor to be able to talk inside the building first time. So very happy to be here. Not my first time to talk at Hatfield. And I always appreciate the chance to come out here and talk to people about the work that we're doing. We have a wonderful team. Underlying name is most important for this talk. That's Dylan Sanderson. He's a PhD student with us. And a lot of the work that I'm sharing today is work that he's been doing for his dissertation. Also joined with Andre Barbosa, John Bolte. These are professors at Oregon State with expertise in structural engineering and also systems engineering. And you'll hear a little bit later in the talk about how we're starting more collaborations with social scientists, including Jenna Tilt and her students, to start to connect the built environment, the stuff that civil engineers like to look at, with the social systems. It's really important when we start to think about the communities and the recovery. Most of the talk today, though, is going to come from our perspective on civil engineering and civil engineering systems, but it's definitely informed by work that we've been doing with colleagues in social science. Let's see if I get the clicker. There we go. All right. So beautiful picture of the Oregon coast. And a lot of us like to look at the sea, the waves, the rocks. But as a civil engineer, I start looking over at the road and the highway and all the infrastructure systems. And one of the really interesting questions is, if there is a large-scale tsunami, what is going to happen to the communities, especially on the coast? And There's a discussion about this sense of islanding. And from a perspective of civil engineering, we're thinking of how communities are cut off from, let's say, for example, the valley, the I-5 corridor, but also within a community, how are people getting from one location to another inside of a community. A lot of this work was informed by a program that was sponsored by Sea Grant. It was called Seed to Leaf, and it involved a group of us going to communities in Oregon. This is way back 2017. We went to Seaside here in Newport, also Coos Bay. The project was led by Peter Ruggiero in College of Earth, Ocean, and Atmospheric Sciences. And it was really discussions trying to hear from different communities on what they felt was most important in terms of Cascadia Subduction Zone hazards. And a lot of discussions started centering around post-event recovery options. So how will communities come back after large events like the Cascadia Subduction Zone? They were asking a lot of questions about the infrastructure. So that's things like not just the buildings, like this building that we're in, but roads, water systems, power, fuel, and communication systems. They were very interested in things like what's best case scenario, what's worst case scenario, where would we likely fall in between. We'll talk a little bit about that today. And then also other talks I've given here on evacuation and life safety, visualization for how to see some of these results. And then the last thing is trying to coordinate some of our work with groups like Dogami and other partners throughout the state. But this sense of islanding was kind of a theme that came up several times in these discussions. And we kind of took all this information back and we kind of centered it on two parts. One was what we called the local connectivity. So this is, you know, if we have this large event, how easy will it be to go from one part of a community to another part of the community? What will the roads be like? And how long will it take me to get from one location to another? And then over time, days, weeks, months, years, how will that system come back? So I'll talk a lot about local connectivity. So that's getting from place to place just within a town like Newport. And then also taking a big step back, the regional connectivity. So that's how we get from a place like Newport out to the I-5 corridor or up or down Highway 101. So those are kind of the two big themes that we tried to put together. And one of the things that I do is computer modeling. And so we built a computer model that would help us look at these two issues of community recovery from a local perspective and a regional perspective. And instead of just picking one community, we wanted to look at as many different communities as we could along the coast. So we ended up looking at all of, not all, but a lot of the communities from Astoria all the way down to Brookings, 18 communities in total. And we created a regional highway map. So this is some work that was done in the Oregon Resilience Plan, where they started looking at the different highways along the I-5 corridor, what goes out to the coast, and then along the coastal highway. The Oregon Resilience Plan has a series of tiered phases for reconstruction. So this is just based on Oregon Department of Transportation estimates of how long it'll take to recover, which roads will be covered first, and so on. So we utilize the Oregon Resilience Plan in our computer model. And we also wanted to identify where are the maintenance facilities on the mostly in the valley, and which coastal towns are assigned which maintenance facilities. So we're trying to pay attention to that. And then we're also trying to pay attention to the airports. So those were just easy for us to identify just on a map where the different airports were. We could have chose something else like hospitals or some other fire stations or some other type of infrastructure. But for the purposes of this talk, we just picked airports because they were easy to identify. And also they're very important for recovery efforts because that's where aid and other resources can come in through the airports. So the roads are tiered based on what ODOT is saying. These are the roads, for example, that would be repaired first. And then the airports are also tiered. And this is based on mostly how close they are to large population centers. So this is just some of the information that we use to inform the model. And then for each of the 18 communities, we also look at all the road network for each of the communities. So all told, probably about 2,000 or 3,000 miles of roads in the simulations that we're looking at. And then we also identify all of the bridges. So this is also easy information to collect from ODOT. And it includes like the bridge over the Yaquina River. So really large, obvious bridge, all the way down to just little tiny bridges that we barely even know that we're driving over as we go on the roads throughout Oregon. We also use the Dogami inundation map. So Dogami has that series of published maps, and we use the large event as our scenario for this simulation. We do damage analysis. So this is you could say like a standard model that's available from the US government. It's called HAZUS. We use this to estimate what's the likelihood of damage of the buildings throughout the bridges throughout the state. This was work that was done by Andre Barbosa and his students. But we subject the state to magnitude 9 earthquake, and we could estimate whether or not the bridges would experience no damage, slight, moderate, extensive, all the way to complete damage. And based on this analysis, the valley has between slight, some moderate damage, but on the coast, it's pretty obvious that extensive damage to a lot of the bridges on the coast. So here's a detail. This is down from Coos Bay. You can see an example. As I mentioned, there's lots and lots of bridges that we barely even know that we're driving over. So a lot of small bridges. Good news is, some of these aren't damaged at all. And then there's some that have fairly extensive damage as a result of a magnitude 9 earthquake. We also can look at the damage of each of the roads kind of the same way. It's a probabilistic model. So you take the amount of ground shaking, and then you just estimate what's the likelihood, what's the probability of that link of road having a certain level of damage that you couldn't drive over the road. So we do mostly just roads and bridges. And then the next step is to, again, try to apply conventional models for the restoration, like how long will it take for a certain link of highway to be restored, or how long will it take for a certain class of bridge to be restored. So these are all based on observations from previous earthquakes that have happened throughout the United States and elsewhere around the world. And these are just, again, probabilistic curves that could be used to estimate how long it will take to restore a certain piece of infrastructure. The one thing that we noticed was a lot of these curves are showing, for example, this is on this axis is ranging from 0 to 1. 1 means it's back to normal, it's in good shape. 0 means it's doesn't work at all. And what we were seeing from this conventional approach is that some of the restoration times were about 1 month, for example, to get a 50% chance that that section of road is recovered. And then within a year, everything is recovered by these conventional approaches, which for complete, let's say magnitude 9 earthquake, we thought that's a little bit unrealistic. So we want to go back and say, what's wrong with these models? Why don't they give us kind of a better result? These are, you could say, trusted models for, let's say, for example, the Napa Valley earthquake. Didn't happen too long ago, but these models show that here's the rate at which that city of Napa is going to recover after an earthquake. But what we feel like is that these models don't account for what's happening up here in the Pacific Northwest because it's so extensive. It's going from California all the way up to Canada. So that was Dylan's job, was to come up with a better, what we feel like is a better model, where we incorporate the Oregon Resilience Plan, what the policies are for how they think the state is going to recover after the event, and then do this tiered approach where we use the curves from the federal model from HAZUS, but we have to step it through time based on the Oregon Resilience Plan. So for example, if there's a section of road out on the coast, but the road leading into it from the valley isn't recovered yet, it just has to wait. And then this one gets recovered. So I think this is a much more realistic plan or model. The other thing that we wanted to do was not just is the road connected, but the real question is, how long does it take me to get from A to B? If I've got, let's say, 3 routes to choose from, and one of them is out forever, it don't really bother me because I can take these 2 other routes. So that I think is, a little bit more realistic. I don't mind driving around. I just want to know how long is it going to take? Is my route from A to B now going to take twice as long, 5 times as long, 10 times as long? So we also switched the conversation from whether or not things are fixed and connected to more of like a personal perspective, like how long will it take me to get from one location to another, even if I have to go down to California and then drive back up the other way. Yeah, so again, this is kind of weighting it based on the travel time it gets from A to B. And since we didn't really have a clear idea, okay, I want to get from this location to that location, we just picked airports, as I said before, because that was kind of an easy thing to pinpoint on a map. But we wanted to make sure we could do every town, getting from either a large airport, what the Oregon Resilience Plan is calling a tier 1 airport, or a smaller airport, like what is right here in Newport, for example, tier 2 airports. And here's the result, for example, for Port Orford. So this is what our model result looks like. We call this the Regional Connectivity Index, and it's a scale of 0 to 1. 1 is good. It means it takes just as long as it normally took to get from, let's say, one location to an airport, a tier 2 airport in the valley. The x-axis is the time that it would take to get to that back to normal situation. The 0.5 here means it takes about twice as long as it would normally take. The 0.2 means it would take about 5 times longer than it would normally take. So this is kind of a measure of how long it would take to get from Port Orford to an airport in the valley. And then the recovery time is on the x-axis. So this is unlike, let's say, the first case where it was showing everything was back to normal after about a year. Here it's after about a year, it's only about 60% of normal. So it's still good. Because of the highways, they're going to have to go around some of the damaged areas. And it's not until about 2 years that things are, you could say, like back to normal in terms of the driving time from A to B. So that was just Port Orford, and that was just for airports. The one thing I want to point out too is that what, the engineer scientists, what we call this range of uncertainty, is each of the gray lines, and there's 1,000 of them, each of the gray lines is one roll of the dice. And we just keep rolling dice, rolling dice, rolling dice, and seeing, how long would it take each of these little iterations for the recovery time. And you can see sometimes could be pretty fast or it could be pretty long. And this blue curve is really just kind of an average. But the uncertainty is anywhere from a month to a year for, if you use this type of analysis. So there is some uncertainty associated with it. It's not a hard and fast claim that it's going to take 2 years for everything to recover. But even with the uncertainty, you can still start to look at different towns along the coast, like which ones you could say like are in better shape or not. And so we wanted to look at each of these towns rather than just do a super detailed study of one town. We wanted to start looking at the relative comparison of different towns. So again, the gray lines are showing there's a lot of uncertainty. For example, here in Newport, for example, a lot depends on what happens to bridges in Newport, for example. But in general, if you compare, for example, Newport and Cannon Beach, they start off pretty good in a sense compared to Port Orford. So Port Orford, for example, the day after, it's about 5 times longer to get to this one location, whereas in Newport, Cannon Beach only takes twice as long. So you can even though there's a lot of gray, a lot of uncertainty with the models, I think we could start to look at which towns in Oregon along the coast are going to have bigger problems relative to their neighbors. That was kind of the point of the study. The other thing too is kind of interesting is the rate at which these communities could potentially come back. For example, if you look at Port Orford, it's kind of that slow and steady trend to come back, whereas Newport, it just takes longer because there's more roadway that needs to get fixed before the roadways close to Newport. So it's nothing happening. Then some of the other roads are fixed, and then things get fixed for Newport, according to this model. So again, it gives you a little bit of impression of not all of the towns will recover at the same rate. They don't all start off at the same level, and they don't all recover at the same rate. Yeah, that's a good question. The reason why it dips is because in the model, we also allow cars to get onto the road, and like a road gets repaired, but then more cars get on the road and it takes longer. So it's like rush hour. So that's, yeah, it's a good question. I thought Dylan had made a mistake, and I'm like, Dylan, find the mistake, find the mistake. He finally convinced me he did it right. It's the rush hour traffic basically in Newport. Newport's the interesting one. It dips on the other axis too. That was the regional connectivity. How do I get from Newport, for example, to an airport in the valley? The local connectivity is, how can I get from one spot in Newport to another spot in Newport? What will the roads be like within just the city of Newport? And how long, for example, with the given situation, let's say, for example, with maintenance facilities in the valley, how long will it take for the road network in Newport to recover? The one thing is, unlike the previous one where we picked airports, here we just picked random locations throughout the town. So we didn't really pick anything special, a school, a hospital, church, or a grocery store. We just picked random spots initially. We're going to change that in the next round, I think. But here's what happens with just trying to get from one location to another location within Newport. How long does it normally take? Would be a 1.0. And then 0 means you can't get there until something's fixed. This is the trajectory, this is the recovery rate. And then within about 1 year, it's less than less than double the travel time. So it's above 0.5. I mentioned too, again, this model that doesn't incorporate the fact that Newport and all our coastal towns are within this much bigger disaster will give us the wrong numbers. Again, it says like within a year everything's fine, but that's not. I think that's totally optimistic. But again, I think the value of doing these kind of computer models, computer studies, is we can start to look at how our different towns might compare, and if there's a way to provide resources for a particular town. Hopefully this can provide some justification. But we can compare, for example, Cannon Beach, Newport, Port Orford. So again, you kind of see they're all starting out kind of low, and then Newport and Cannon Beach, they seem to recover a little bit more quickly, Port Orford a little bit more slowly. And we can combine these two. So the local, the regional, we can combine them, and we can just see how would things change over the course of a year. And we can compare, for example, some cities like Cannon Beach and Port Orford, even though there are definitely differences within each of those towns, but you could say in general, they're better off in terms of like getting from their town outside. and then not as good getting around within their town. So their regional resilience is better than their local resilience. And then other towns like Toledo, it's the opposite story. It's getting within the town is going to be, compared to the other towns, easier, but a little bit harder to get to some of the regional locations. Okay, one question, I think the other thing too, the nice thing working with that stakeholder group early on was, okay, some solution, some like, what could we do? What would make it, what would change the recovery times? And so what we're looking at here, for example, is if, for example, instead of requiring going from A to B outside of a town to, let's say, tier 1 airports, if, for example, these second-tier airports would also provide the same value for a community to recover, then some places like Cannon Beach, Rockaway Beach, it doesn't make a difference. The airports are all the same. But if you look here in the Central Coast, there's a big difference between these airport types. And so I think this would point to like the importance, for example, of the Newport Airport, Siletz Bay for the regional recovery for the Central Coast. That's how we're interpreting this one. I think another big question for us was noticing that all of the ODOT maintenance facilities were all along the valley. If the maintenance facility were located on the coast, how would that change that towns or the towns near that maintenance facility, the rate at which they could recover from the event? Some places like Manzanita, it definitely, and Cannon Beach definitely made a difference. If the maintenance facility is moved out to the coast, definitely makes a difference. For some of the Central Coast locations, it didn't really matter. And then when you get to the Southern Coast, it seemed to matter again. And it might be hard to see, but it matters from like years, like from 2 years down to like a few months. So again, these are just computer simulations, but it seems like there would be a good argument, or at least for more study, like, well, what if some of these maintenance facilities could be located out here? That could potentially make it much faster for some of these communities to recover. So that's kind of a main takeaway from our study. Press release, we're very fortunate to have Adriana Coet-Crone from Sea Grant. She saw the report that we wrote and talked to people at OSU Marketing and Relations to write a press release. They wrote up the research in a really nice, excellent, understandable way. It got picked up by several outlets, including Coin 6, some of the other papers. The United Nations picked it up. And then we also did some interviews with public radio. So it was really nice that, there's, I think for me, the thing I got out of it was there's definitely a lot of interest in trying to think about this event regionally and what are some of the things we could be doing to increase the resilience and the connectivity of these different communities. Last slide here, second to last slide. This is our next step, is more work with the community. So trying to talk more about, rather than just kind of random locations from A to B, let's start talking to the communities about what they identify as the assets and the needs within a community, and then start looking at those particular locations. So I think a little bit more intentional work with the communities on their identified assets and needs. So that's starting this fall. We'll present more of this at the State of the Coast meeting in November. Summary for this project, it's really a huge thank you to Sea Grant, the Seed to Leaf. It kind of changed the way I like to do research now, where talk to stakeholders from the beginning rather than just show up at the end. I think that something we learned really early on is that some of the conventional models are not likely to work for our issue because they were built for something different. Like say, for example, a smaller, I would say self-contained earthquake like Napa Valley. But if we're looking at regional issues, I think we have to be a little bit careful. And but I think we're making some progress on trying to understand these two issues: regional connectivity, local connectivity, and next steps for us on regional. I think we're going to start looking a little bit more at access to healthcare rather than airports. That was some feedback we got, and then on the community identified assets within a town. So that's kind of our next steps, and that's it. Thank you, guys.
All right. I think we're going to have questions. So
Okay.
we'll start to see if there's any questions online. Go ahead.
Yes, do the recovery times account for the time for federal and state funding to materialize?
That's a great question. The answer is no, we didn't. But that could be done, but we didn't do it. That's a good question. Thank
Great.
you.
Any questions in the room? We'll take turns here. All right, hang on.
So I'm curious about more specific details about Newport in particular.
Sure.
Like, I'm sure everybody in the room is.
Yeah.
Like, does your model assume the bridge 101 bridge goes out? And I'm also curious about Highway 20. That's got lots of bridges, and is bridge vulnerability mostly age or size, or just got lots of questions like that.
Yeah, it's a good question. I would have to phone a friend on that one with Andre, but the variability in these gray, some of this is likely due to the bridge, whether or not the bridge collapse or doesn't collapse. So there's like a probability that it could collapse for, let's say, magnitude 9 earthquake. Sometimes when I talk to people, they say, oh, it's all going down, it's all going down. Well, it doesn't necessarily, it's a probability that it does. And I think some of this is that, the probability that it does go down or doesn't. But I can't say without checking with Andre for that particular bridge. It's a good question.
All right, we're going to take turns. Question online.
Yes, does this just consider the state, county, and city roads? What about all the logging roads that would most likely be options, especially with all the heavy equipment in private hands?
That's an awesome question. We did not include any logging roads, but that's a great question. I'm going to write that one down. I didn't even think of logging roads.
So it looked like from the model that even right after the earthquake, supposedly people from Newport could get to the Eugene airport. Is that really a likely thing to have possible? It seems like it wouldn't just take twice as long to get to the Eugene airport right after. I think it would be impossible because there's going to be some parts of Highway 20 that are out.
Yeah, thank you for bringing that one up. In addition to not including logging roads, we did not include landslides. Yeah, so again, this is just a study. It's not actionable information. We were really just trying to look, is there a difference between the different towns? That was kind of the scientific piece of it, rather than trying to advise the state, here's what is going to happen. I would say if we included the landslides, we're probably going to see a different picture. So that's a good question.
All right, online.
Okay, I'm curious whether your models incorporate seasonality as well. Would you expect there to be any difference in the severity of the disturbance impact or the pace of recovery in the rainy season versus dry?
Yeah, that's a great question. I would say in general, there's no seasonality here. For example, we didn't incorporate landslides, more likely to happen in rainy season. We didn't have anything like that. And on the recovery, we didn't say like, okay, if it happens in the summer, it's going to be easier or more difficult to rebuild the roads. We didn't include anything with seasonality. I think this, I know it might sound strange. This was probably one of the biggest things to come out of our study. That dashed line is what, let's say, what is called HAZUS. It's kind of a very standard model for looking at hazards. A lot of counties use it for looking at debris generation, that kind of stuff. I think one of the most important things that we got is we can't use conventional models. They're just not set up for Cascadia. So we're going to try to build our own one step at a time. And I think the comments we're getting back are really good. Like, what about logging roads? What about seasonality? So I think these are going to help us to build a model. I think from a, let's say, a damage engineering perspective. And I hope we're also going to get comments from people on, did you consider, I don't care about airports, I want to get over to the fire station or things like that. So I think where the two locations would be, I think is hopefully going to come out when we talk to folks on State of the Coast. But yeah, these are fantastic questions.
I'm sorry if I missed this in the beginning, but is this just the effects of the earthquake, or does this also involve effects from tsunami?
Both, yeah, has both. Yep. The tsunami one was the Dogami L. So we just picked the L event. So this was for Newport. You guys are all familiar with that one. And I think the other one too is you guys are, you have heard lots of stuff on tsunamis already. There's different likelihood of an event. It could be smaller, 8.5, could be, and we didn't do anything where we start to look at the different types of scenarios. We just picked one and went with it. So I think that's, I think the work will continue. Maybe we can start to look at the different scenarios, but I think the main thing we wanted to do is just, what's Brookings like compared to Astoria? Like, is there a huge difference between the two, or are all the cities in the same boat? I think that was the first cut, I would say. And I think our work is showing like, yeah, there's some differences in the cities, even ones that are only 30, 40 miles apart. And I think just the nature of our coast and the way the highways are set up.
All right. If you are online and you have questions, go ahead and put them into the chat, and questions in the room.
Just a question in regards to the model as it pertains to bridges here in Oregon. I know as it was presented, it looked like you had qualified the different sizes of bridges, but as we all know, like aging infrastructure, was the, I guess, quality of the bridges indicated as well?
Yeah, and so the way the damage works is you have a bridge type, and then a selection, what we call fragility curves. So each bridge type, each archetype has to have, a certain set of curves associated with it. And what goes into the bridge type is, is it date of construction, connection details, all the standards for the bridge. There's actually a lot of work done on earthquakes and bridges. So that's actually, I think, one part of the model we're pretty confident about. That one, with some possible exceptions, like the Quinnabre Bridge here is kind of unique. There's probably not a fragility function specific for that bridge. So that one probably has a much wider uncertainty. But let's say a, typical federal highway, AASHTO bridge, something like that, those damage functions are pretty readily available. A little bit less so with the tsunami. So if it's in the tsunami inundation zone, I think that's got a little bit more uncertainty with that one. So let's say, for example, Seaside, for example, lots of bridges up there.
All right, we got a question online. Go ahead.
Okay, what is your hunch as to how significantly landslides would affect the results?
I think it's going to be important for sure. Yeah, that's, I think, on the to-do list.
All right, questions in the room. Hang on just a second.
You guys are asking great questions. Make me a little nervous though.
Sorry, don't be nervous. Does your model consider access to the ports by sea?
No, yeah. You guys are asking great questions, but no, we haven't incorporated any of the access by sea. I think one of the hard parts for us is, unlike, let's say, bridges, for example, where there's lots of earthquake information about damage to bridges, there's very little information about what would happen to the jetties, for example, the port infrastructure. That for the case of a tsunami, there's just not as much to go on. But I think that, yeah, that could be added in the future for sure. I think it's these conversations that kind of motivate us, and, you know, State of the Coast, or when people start saying, well, you know, this should be included in the plan. I think especially for the coast, if it turns out that, you know, these recovery curves, if these could change in here, if we start to consider ports, then, you know, maybe that's something that we need to bring into the study. So that's an excellent question.
I was wondering if you have thought about looking at Japan and applying these kinds of models there, where they already have the answers for how long it took to recover.
Yeah, that's a really, really good question. I actually was, I lived in Japan when the tsunami hit. I was there for about a year. And I took a lot of visits to see what the damage was. I took a couple trips later to see the recovery. So it's definitely something we could draw on. I think the hardest part for us is getting the data, not of the recovery, but like the as is. Whereas for us here, we can get all the information on the streets. We, you know, it's just easier. Still had to do a lot of work, but it's, it's a great question. Yeah, you've already, like, my to-do list now is already like 10 items, but I think it's a really good point, because I think let's say the engineering of that infrastructure and our infrastructure is very similar. So I think it would lend a lot on recovery times, recovery rates. So I think we should. It's just, yeah, write that one down too. It's a great idea. It definitely. Thank
All
you.
right, we got a question online.
Okay, you mentioned working with social scientists in the future. Could you tell us a little about what you hope to do together?
Yeah, perfect. Yeah, this our social scientist on the lead on the project is Jenna Tilt. And what she's interested in doing is talking to the communities and trying to identify the things that they care about. So again, as engineer, usually we write down critical facility and we just, you know, where's the fire station? Where's this? Where's that? But it doesn't mean day to day, that's where, you know, everybody wants to go. And so I think, let's say, for example, if there's a community and they value, for example, a civic center, a place to gather, or, you know, they've got questions about food security, then that's what we want to bring into the model, rather than just what I would see as important as a civil engineer. Oh, you need this, you need that. So I think the social scientist is really to talk to the community and to get their values, to plug those into our model. I think, yeah, that's probably the main thing. Go ahead.
So my gut feeling is that recovery is going to take longer than your model says. So I keep thinking about the bridges, and, you know, let's say Highway 20 has 3 bridges that are damaged and can't be used. And that's happening to all the roads from the valley to the coast.
Yeah.
And so does your model take into account that all this is trying to recover at the same time? Because I just can't believe that
Yeah,
all the
so,
bridges would be repaired within a year or two in the whole state. You know?
right. So, yeah, so it's a good question. So what our metric is can you get from A to B? But there might be lots of different routes to get there. And so let's say, for example, the Oregon Resilience Plan has prioritized a certain route. If that route's open, then you can presumably get from A to B, but it's not saying that C, D, and E will also be repaired. Yeah. So that's, yeah, yeah, exactly. And so I think, yeah, I'm not putting a ton of stock on the x-axis, but what I'm interested in is whatever mistakes we make, let's assume that we're making them equally for all the communities, which community's trajectory needs the most work. So that's kind of the way I'm looking at it for now. I think all the comments that you guys brought in, like, well, what about landslides? Or on the plus side, what if we bring in port facilities? I think that could potentially change it. But right now, I think the best we can use our model for is, number one, say we don't want to use canned software because I don't think it's going to work. And we can say that there are differences among those communities. And probably this last one, we have some conversations we're hoping to have with ODOT. This area in particular, if the maintenance facility is moved out to the coast, maybe there's other reasons to move it out on a, let's say, day-to-day basis, then it could potentially have a pretty, very positive impact on the recovery of those communities in the south. Whether or not it actually goes from 2 years to 1 year, whatever, I wouldn't trust the numbers perfectly, but at least the arrow is going in the right direction. That's probably the best you could get out of the computer model.
So I had a question kind of for the audience as well. Has anybody heard National Guard Station, the response that they're expecting after the event here? We're just thinking about other things that might influence an individual community's response. We have a National Guard station here that has large earth moving equipment. It is on the coast.
I will write that one down. I'm learning a ton coming out to you guys.
And I just don't remember if others had talked to the National Guard as part of their response to see where we fit in the tiered response. But I'm going to hand
Good.
this to Lori.
So I had a question about whether the road department can use your information to identify what are the weak links. It looks like the road between here and Corvallis, because it has all new bridges on it,
Yeah.
looks pretty good.
Yeah.
But we all know there's 1 or 2 old bridges that are still existing, and those ones would then be the problem, or a road section that's unlikely to last. And whether then you could use your model to help prioritize for the roads department to say, hey, this is a bottleneck, or is going to be a bottleneck.
Yeah, we hope so. So for the State of the Coast, November 5th, it's going to be here. We're so very excited for that meeting. We have about 75-minute panel discussion, and we'll kind of simplify this for the panel discussion. But we did get ODOT. They agreed to come on the panel. LCDC is going to be on the panel. One of the president of the Oregon Seismic Policy Action Commission, OSPAC, they're gonna be on the panel, and so hopefully we do get that conversation going about how they might be able to use these results, or we can add to it, add the good ideas that we heard today. But yeah, I think in general it's that the prioritization, or if they make a prioritization, what does that mean for the other communities on either side? I think that's also important information too.
Other questions in the room? All right.
I think we have to also be concerned about who is in politics at the time. The National Guard coordinating with FEMA and ODOT, their response time, and integrating that data seems, unfortunately, all too important.
Yeah, that I think is similar to the first question. Like, did we incorporate yeah, the federal response and all that kind of stuff. It's a very good comment, very good question, but yeah, we didn't incorporate any of it.
I'm going to put Tracy on the spot for a sec. Can you talk to us about registering for the State of the Coast if we want to join the conversation that Dan's been talking about?
Sure. As far as I know, there are still spots open to register, and you can register online through Oregon Sea Grant, our website. It's $40 registration. That gets you your refreshments in the morning and lunch, as well as there's a bunch of other activities that are going on besides just this panel. So I would highly recommend that anyone who's interested come and join us.
Great. We're going to throw it out one more time before we let Dan go. Any other questions in the room? Any other questions online? Dan, you have any wrap-up questions for us?
I have one. Well, first of all, I want to thank you guys because I'm never 100% sure talking about tsunamis when I come out to the coast. So I really like the audience and I really appreciate the feedback for sure. I love coming out here to Hatfield. So huge thank you for inviting me and being able to talk. And a big shout out to Sea Grant. It was a really interesting way that they said, let's start this as a seed project. We're going to grow it as a bigger project. Now it's been taken on by NSF with Peter Ruggiero at the helm. So it's kind of growing. And yeah, just a huge thank you to Sea Grant for getting all this stuff started. And thanks for all you guys.
All right. One more thank you. All right, everybody. We'll see you next week. And again, thank you so much, Dan.